Currently, an object from another star system, known as Tri-I/Atlas, is rapidly moving through our solar system, doubling its brightness every few weeks and forming a green cloud 500,000 kilometers wide, heading towards Mars. Astronomers expected just a flicker, but instead, Tri-I/Atlas now shines 6 times brighter than anticipated, baffling Earth-based telescopes and sparking urgent debates about the true cause of this outburst. A hyperactive core, alien substances capable of unlocking sunlight, or something even stranger. With the approach to Mars expected in a few weeks and visibility from Earth soon to be obscured by sunlight, the race to uncover the truth has begun. Before Tri-I/Atlas leaves our reach, it's important to understand what drives this unprecedented phenomenon and what secrets are hidden within this glowing coma. At this moment, Tri-I/Atlas is about 2 astronomical units from the Sun, which is twice the distance from Earth to our star, or approximately 300 million kilometers. His speed is astonishing. He moves at nearly 60 kilometers per second and continues to accelerate. When he gets closest to the Sun at the end of October, his speed will peak at around 68 kilometers per second. In comparison, it is more than twice as fast as any other planet in the solar system, and enough to cover the distance from Earth to the Moon in just over an hour. On the brightness scale, Tri-I/Atlas reached 12th magnitude. This number may not seem significant at first glance, but in practice, it indicates that the comet is out of sight of the naked eye. Even experienced observers will need at least a medium-sized telescope, and only under dark sky conditions. In fact, the difference between the 6th magnitude, the threshold for human vision without aid, and the 12th magnitude is about 250 times dimmer. Yet, despite these challenges, its visible brightness increases much faster than any models predicted. Coma, a cloud of gas and dust surrounding the core, has grown explosively. Recent measurements show it now spans several 100,000 kilometers, rivaling the diameter of Jupiter. This expansion is not only a visual spectacle, but also the key reason why telescopes capture more light from the comet than expected. As the coma grows, more sunlight is reflected and scattered, increasing the measured brightness of the object, even if the solid core remains hidden. Every major research and observatory tracks this data. The Atlas team, which first noticed the object in early July, records each new position and brightness update in real time, filling trajectory models and notifying the small planet center of any sharp changes. Considering the flyby of Mars and perihelion, these rigid metrics, distance, speed, brightness, set the foundation for all that will follow. In September, Tri-I/Atlas exceeded expectations, showing a burst of brightness. The light curve, used by astronomers to track how an object brightens or dims over time, sharply deviated from the predicted path. It was not just a slight increase in brightness, but a sharp jump that sparked heated discussions among both professionals and amateur astronomers. At the center of the mystery is the comet's coma, a vast cloud of gas and dust surrounding its hidden nucleus. As the comet grows, it reflects and scatters more sunlight, making the entire object appear brighter in telescopes. By early October, the window for observing Comet 3I Atlas from Earth is quickly closing. Every night, the comet descends lower into twilight, closer to the blinding light of the sun. The angle between the 3 eye slashes of Atlas and the sun, which astronomers call solar elongation, decreases to 30 degrees by October 21st. This is the threshold at which even the largest ground-based telescopes struggle to separate the faint light of a comet from the dazzling brightness of the sky. For most inhabitants of Earth, the practical window for observation has shrunk to a narrow strip of time just after sunset, when the comet barely appears above the horizon before vanishing into the haze. Amateur networks rush to capture the last usable images. Online forums are filled with messages about failed attempts and rare successes, while observers hurry against the approaching twilight. Some teams coordinate global campaigns, passing observation duties from one longitude to another in a relay, hoping to capture a few more frames before total darkness. Professional observatories, constrained by stricter safety requirements for their sensitive optical systems, have already begun to reduce observations. The risk of damaging equipment by pointing it too close to the sun is real, and few are willing to take that risk. The urgency is not only related to the loss of photographs. As soon as 3I/Atlas passes behind the sun from Earth's perspective, a complete blackout of data will begin. There will be no direct measurements, spectra, or any way to track changes in brightness or structure. For astronomers, this means that every remaining observation until October 21st is critically important. The geometry of the solar system closes the door, and the comet will slip out of reach just as it approaches its most active phase. The only hope for continuing observations will come from objects far from Earth's line of sight, which becomes a task for spacecraft orbiting Mars. For a brief period, Mars becomes the only outpost with direct access to 3I/Atlas. While ground telescopes lose the ability to observe in the blinding light of the sun, attention shifts to a fleet of orbital spacecraft orbiting the red planet. Each mission brings its unique perspective. Mars Express of the European Space Agency, equipped with a high-resolution stereo camera and the Omega spectrometer, can capture both images and chemical traces from millions of kilometers away. The ExoMars Trace gas orbiter, equipped with NOMAD and ACS spectrometers, is designed to detect faint traces of gases, water, carbon dioxide, and even exotic volatile substances in the coma of a comet. NASA's MAVEN, designed to study the upper atmosphere of Mars, can adjust its ultraviolet spectrograph to capture gas and dust emissions from a comet, while its plasma instruments track how solar wind interacts with this interstellar visitor. The Martian Orbital Probe, known for its clear and high-quality camera, can resolve the core of a comet if conditions allow. Although tracking a fast-moving comet is a challenge for any spacecraft, the geometry favors Mars. On October 3rd, Comet 31/Atlas will fly at a distance of about 28 million kilometers from the planet, close enough for orbital devices to attempt direct observations, yet far enough to avoid dust hazard protocols that previously hindered comet observations. The instrument team spent weeks conducting simulations, updating ephemerides, and coordinating precious observation slots. Each team wants to secure its share of this event: visible and infrared images for mapping the coma, ultraviolet spectra for measuring gas emissions, plasma data for studying the interaction of the comet with the solar wind. The hope lies in capturing the core as a distinct point, separate from the sprawling comet, and determining the chemical composition of the material released as the comet heats up. No mission promised continuous coverage. Observation plans depend on the limitations of spacecraft orientation, data bandwidth, and the unpredictable timing of the comet's closest approach. But even a few successful passes can provide knowledge unattainable from Earth. Direct measurements of dust, gas, and plasma on a scale never attempted for an interstellar object. At the moment, attention is focused on Mars, and scientific teams are ready to seize this rare opportunity before the 31/Atlas rushes to meet the sun. The first thing that catches the eye about the 31/Atlas is its bright green glow. Spectral analysts quickly focused on this color, examining the light of the comet for chemical signatures. The consensus, supported by ultraviolet spectra obtained from both professional and amateur teams, points to diatomic carbon, C2, as the main culprit. When sunlight hits carbon-containing molecules in a coma, it excites them. As these molecules relax, they emit bright green light, especially in the swan bands around 510 nanometers. This is a classic signal for active comets, but 31/Atlas stands out with its intense green hue, even at a distance of 2 astronomical units. Not everyone agrees with the details. Some teams noted the possible contributions of ionized carbon monoxide, CO+, or the cyanogen radical, CN, especially in the early spectra of September. Both of these objects can glow green or blue under sunlight ultraviolet, and scientific circles have sparked debates about calibration scripts and background processing. Nevertheless, the most reliable datasets with clean and broad spectral coverage consistently show that C2 hydrocarbon radiation dominates the visible coma. Here, chemistry is not just a visual effect. The speed of the Tri-I/Atlas comet means that solar radiation strikes the new ice and dust with force, tearing volatile molecules and mixing them with the coma. As a result, the green color not only signals the presence of carbon, but serves as an indicator of how quickly the comet's surface changes as it moves toward the sun. An increasing number of observers began to notice something strange about the appearance of the Tri-I/Atlas. A light streak directed toward the sun stretched backward. This so-called anti-tail structure contradicts what most people expect from a comet, where dust is usually carried away from the sun by radiation pressure, forming a classic outward-pointing tail. In the case of Tri-I/Atlas, geometry and physics work in such a way that everything happens in reverse. When a comet moves through the inner part of the solar system at extreme speed, like it is now with Tri-I/Atlas, particles of dust ejected from the nucleus can actually move ahead of the comet's trajectory, especially if they are large or charged. From the perspective of Earth, these particles can form a narrow, sunward-pointing spike, an anti-tail that is visible only at the right angle. Plasma physicists point out that the rapid expansion of a comet's coma, combined with the high speed of the comet, creates a complex environment where electromagnetic forces compete with gravity. Charged particles of dust between the solar wind and the comet's ejection can be focused into narrow streams. These solar features are not constant. They depend on the interaction of particle size, their charge, and the constantly changing direction of sunlight. The effect is enhanced by the unique geometry of observation at the end of September, when the Earth is almost in the plane of the dust cloud Tri-I/Atlas. Currently, reports of the solar anti-tail Tri-I/Atlas remain preliminary. Astronomy enthusiasts and some professional groups noted possible hints, but no peer-reviewed photographs or precise measurements have been published yet. The phenomenon is not new to comet science, but its appearance on an interstellar object at such speeds is rare. At this moment, the anti-tail adds another intriguing detail to the already unpredictable visitor, hinting at the complex plasma physics of dust unfolding as the Tri-I/Atlas approaches the Sun. Each comet visiting our solar system brings its own features, but 3AI/Atlas stands out even among rare objects. The first two interstellar visitors, Oumuamua and 2II/Borisov, set the expectations for astronomers. Oumuamua, discovered in 2017, turned out to be a dry, cigar-shaped object without a visible coma or tail, simply a rotating fragment that passed through the inner part of the solar system almost unnoticed. 2 years later, an object 21/Borisov appeared, exhibiting all the characteristics of a classic comet: a bright coma with a blue hue, a tail of dust like from a textbook, and a chemical composition dominated by water and cyanide, like icy wanderers that orbit the Sun every few centuries. However, 3E/Atlas does not fit into any of these categories. His comet is not only large but also unusually green, a result of a strong emission of diatomaceous carbon, not seen in such volume in most comets of the solar system. The increase in brightness, nearly 6 times exceeding forecasts, has no parallels in the modest movement of Oumuamua or the stable ascent of Borisov. While Borisov's tail stretched from the Sun as expected, 3E/Atlas hints at a reverse tail directed towards the Sun, a line more familiar to the rarest comets of the solar system, but almost never seen in interstellar objects. Even among the recent newcomers, such as C/2025 R2 Swan and 6 Lemon, who have shown their own bursts of activity, 3E/Atlas stands out. His speed, chemistry, and unpredictable behavior force astronomers to reconsider the boundaries between comets formed in our solar system and those formed in distant planetary systems. For classification groups, the task is not just to assign a label. Each anomaly in the behavior of 3E/Atlas opens a window into the physical processes that could have shaped small bodies throughout the galaxy. The stakes are high. Each new dimension could overturn decades of assumptions about what it means to be a comet and what stories these visitors might tell about the worlds they left behind. After perihelion, 3E/Atlas will begin to dim, likely much faster than it brightened. Most models predict a sharp decline in visible magnitude as the comet speeds away from the Sun, with the coma compressing and dispersing into darkness. For those hoping to witness this spectacle, the requirements become increasingly stringent. A telescope with a mirror of at least 20 centimeters becomes the minimum requirement. Even then, only the most sensitive digital cameras can capture just a faint shift. Visual observers will lag behind the comet's rapid departure, while image overlay and careful background subtraction will be necessary to track any remaining activity. The practical side of observing comets is now shifting to online boards and coordinated campaigns. Networks of citizen science, some built on Discord servers and others organized by established groups, provide updates on the comet's position, brightness, and morphology almost in real time. These platforms gather raw data from the backyards of telescopes around the world, process it through shared channels, and publish light curves that anyone can track. For many, this is the first time the fate of a truly interstellar object is recorded by amateurs almost in real time. The stakes for science do not end with the disappearance of the object. Each new data point, each light curve, each spectrum, and each controversial discovery contributes to a larger picture. How do interstellar comets behave as they pass through a solar system so different from their homeworld? What can their chemical composition, dust, and fading glow tell us about the building blocks from which planets were formed throughout the galaxy? These questions go beyond the field of observation, inviting anyone with a telescope, laptop, or just curiosity to join the search for answers until the Tri-I/Atlas returns to darkness. As observations from Earth become impossible after October 21st due to superior conjunction, the flyby of Mars on October 3rd becomes the last opportunity for close multi-instrument observations. Detailed mission schedules of Martian orbiters have not been published, leaving gaps in our knowledge of upcoming data. Unlike Oumuamua and 2I Borisov, 3I Atlas shows a combination of cometary and unusual characteristics. What will happen when it passes by the Sun? Its composition, decay rate, and structural behavior will provide the key to future research on interstellar visitors. For now, the true nature of the Tri-I/Atlas remains an open scientific question based on hard-to-obtain evidence and awaiting the next close encounter.